Okay, it's let me yeah, no, so sorry, that I should not have done. Okay, yes, this is a point. Okay, it's very nice to be here, and it's very nice to be here to give really my best wishes to Sergio. I will try to tell you a bit about the, say, mainly numerical activity, very connected to experiments. So I will try to give something about you. But again, my first point is about Sergio test script. And happy birthday to Sergio. And really many happy returns. I wanted to say, I've been very happy in physics. Physics is a lot of fun, and you meet a lot of wonderful people, and many of the people I meet are here. But then friends is a bit different, and I really count Sergio among the very good friends I found in this field. Not very many, because again, friend is something deep. And maybe since we were so young when we met, right? I think we were in Paris in '82. I was in Saclay. I think you were in EHS at the moment. And there was a lot, right? There was Paris, there was Saclay, ENS, EHS, Orsay, restaurants we loved very much in town. Excellent physics would be all around us. And it was kind of paradise, right? And being very so young, that was important, obviously. And Giorgio, that was frequently like us. So I really remember that as a wonderful period. And again, meeting Sergio was one of the nice things of this period. I wanted to show this picture because it's beautiful. This is from Rome, from the Giorgio Parisi feast. It shows how important it is to be able to pay a lot for a photographer to have a beautiful picture. This is a professional photographer that took this one. Okay, Sergio is very beautiful as usual. You don't need to pay for that, but still, all the frame is fantastic. And again, Sergio, really very happy birthday. So in the minutes I have for this talk, I want to talk, okay, I would say about disordered fluctuations. The framework is Parisi theory, and the field is spin glasses. Even if a lot has been done, and I mean, right, spin glasses can be read in a very extended sense. The talk we had before was a talk that clearly comes from this kind of framework. Even if we are in a situation now where we understand a lot, also thanks to mathematicians, as we've seen, still there is a large number of open problems. Really many. And somehow, say one is when you really want to try to understand, because this is still a problem, when you descend from infield theory to the real world, how much is left of this structure and how much this structure is predictive for this kind of materials. Clearly, that can be not maybe the most important point, but is an important point. And what happens when you apply a magnetic field and this kind of problems. In this discussion, numerics has a very important role. Even if, even numerics here, it is very difficult because the complexity of these systems emerges in, say, a number of features that kind of block numerical. Right? Many of you know everything about it. Even usual Monte Carlo would not work if you wanna try to study the equilibrium distribution. This is not what we will do here. Here we will be involved with dynamical processes. You need to get improved Monte Carlo, you need to do something better. And it's very difficult as analytic approaches are. Renormalization group, I mean, there has been a lot of work on renormalization group, De Dominicis, Condor, Temesvari, many others, but still it's very difficult to keep that under control. Also, I want to say that there is a strong innate taste, say, for numerical computation by some of us. This is all connected also to this huge activity that's been around this kind of statistical mechanics or disordered system group about building optimized computers and all the software tools that are needed to make them work at best for our specific problems. Indeed, there are at least two big experiences that are relevant in what I'm going to tell you. And so I want to quote them. One is the ape computer. So ape is because this computer was supposed to be maybe not very clever, but very, very powerful. That was the idea of the way we built this computer. That was really promoted by Nicola Cabibbo and Giorgio Parisi, started in '84, basically ended in 2006. And it was mainly conceived for lattice QCD, but then eventually we found out that it was a very good tool also for studying spin glasses. So for example, I will show you here some results from '95 that use the computer, API computer, and that tell you what happened. This has continued, and I will show recent results in which this computer is used by an Italo-Spanish collaboration with mainly Victor Martin Mayer in Madrid, Juan Ruiz in Badajoz, Alfonso Tarancon in Saragossa, and us in Rome, Raffaele Trepiccione in Ferrara, the Janus computer. This has been from the start a computer mainly dedicated to study spin glass physics, built in a very peculiar way around FPGA. So this is one, and also this kind of innate taste also goes from to algorithms, meaning that in many of these situations, there has been a lot of thinking about optimizing algorithms. So from the contribution that has been given to tempering, to pseudo-random number generation, to modify Langevin equation, algorithms, and so on. Okay. So at the end, I will be able to discuss with you about very large scale optimized numerical simulation. And I will discuss them in contact with modern experiments on spin glasses. That is my main point today. We are going to go to that. Okay. That use basically this hardware innovation and the software innovations that I will tell you. Okay. So these are mainly the two basic points of my talk. So I would like to communicate them to you, because I think these are things that really have improved our way to understand things. So when you try to understand spin glass physics, and here I'm talking about finite dimension, right? So in some sense, all the beauty of the mean field Parisi solution tries to be there, but we don't really know if it's really protected from this descent to the real world. And things are very difficult. I mean, mathematics does not help at all, as it does for infinite, for mean field theory and so on. So, point one, numerics can and must learn a lot from experiments, and somehow the other way around. This will be one of the points. It's very difficult, it's never trivial, to connect experimental results to numerical results and to theoretical results. Mainly there is a point that is typical. There are 2 points. One is about scales. Typically, the scales you can explore experimentally are not the same. You can have time scales, distance scale, we are going to see that, are not the same you can explore numerically. Right? And so you have to be very careful to it. The other one is about protocols. So you have to try to understand what you can do in one framework in order to have other framework matching. And I think that if I succeed to communicate that to you, this will be my main point. I will try to show you that today we have been able really to match, I will discuss with you a test case, to match these two reality, and so to really learn something. Also, the other point that I will discuss here, that is important, is that the correlation length, when you go to low temperature in disordered systems like spin glasses, so system with quench, frustrated disorder, where couplings can be both positive and negative, and where frustration plays an important role in deciding the physics of a problem, grows very slowly. So even when you sit in a situation where at equilibrium, you expect to have an infinite correlation length, when you do experiments, even waiting years, because we know that spin glass physics is a situation where you have aging and where after years, things are still evolving, even if a very hidden way, okay? Even in this situation, even in this situation, the correlation length is typically very small. But it's somehow nice because it tells you that at the end of the debate about the equilibrium distribution could be a bit less relevant of what we believe at the start, because if at the end you are looking in reality at systems that have correlation length of 100 spins, then okay, this is what we are interested in, right? Also, and this is a corollary of my second point, measuring experimental correlation length is very difficult. This is easy experimentally because correlation functions are something you access directly in a numerical experiment, but in real experiment, this is very difficult. So I will try to explain you how experimentalists succeeded, for example, to do something like that in spin glasses. And again, I believe this is interesting because of the consequences of that. Okay, so I will try to do 3 points. So this is my summary. I will start with a paper of ours from 95, 27 years ago. And why I will do that? Because I want to show you that this paper, I will not discuss all paper, just a feature of this paper, led experimentalists to introduce a measurement technique that allowed to access correlation lengths experimentally. And also that this measurement of the correlation length turned out to be very compatible with what we found numerically. So 95, yes, 95 numerical measurement of psi by using dynamical methods. I will show to you 99, a collaboration of French and American experimentalists not adopt this method, but use some techniques they very smartly invent in order to obtain the same result. And they find that there is a good coincidence. And then I will go to recent work. It is indeed joint work from our group and part of this experimental group in 1999 got these results. Now techniques are very changed, both experimentally, I will tell you something, both numerically, and we can go very far. And I will try to show that there is indeed a deep agreement. And this has potentially many consequences. Sorry for the S missing. Memory, temperature, chaos, structure of states. If I will have a moment, I will just tell you something about that. So we start from a numerical result from 95. It was a paper by Parisi, Retort, Ruiz Lorenzo, and myself. Okay, the paper had a strong ambition, you see the title. I mean, we even succeeded to publish it on Physical Review Letter. That was kind of impossible. A numerical evidence for spontaneous broken replica symmetry breaking in three-dimensional spin glass. But I don't want to, so it was a paper that was really dealing with both the static of the system, equilibrium distribution, and with dynamics. I don't want to go in that. I don't want to go in that today. But what I want to discuss is about one part of this paper. That will be this dynamical determination of the correlation length. So we're talking about a three-dimensional Edward Anderson spin glass. And here we're using this APE computer. Okay, it was a computer done for doing quantum chromodynamics. You see, our idea was a bit similar to what GPU are now, right? The idea was, but since for doing a rotation, we use a matrix, and so we use many times the numbers that we build, that we bring in our processor. Okay, we can indeed conceive an hardware structure that does that very effective, because at the end SU3 It's a kind of rotation somehow. But then we find out that with swing glasses, we can do something very similar, because once we bring a coupling to the processor, then this coupling will be used a number of times. So if you organize the computation smartly, you can do that, okay? And we use APE for a few years, and that was interesting, gave a lot of results. So in this paper, we do both static analysis by using optimized Monte Carlo method, I will not discuss it here, and dynamic analysis. That is what I want to discuss. So our idea was to check how Parisi replica symmetry breaking theory would be consistent with numerical experiments in this case. And then we look at overlap correlation function. No, I'm getting overlap correlation function. So overlap is how similar are typically two systems. Sorry, I'm not giving the basic definition, but I'm assuming that they are general knowledge here. But what you have to do, what you want to do here, is to compute that only for configurations that have a small value of this overlap. So configuration that's somehow different enough. In order to do that numerically, typically, experimentally, you are exactly the situation, but that will not be very important. It will be doing this analysis dynamically. Basically, you say, I use a very large system, a system where I could not talk to equilibrate, where I stay far away from equilibrium, very far away. I take two configurations starting from a completely different starting point, and I see how they evolve. If a system is large enough, they will not approach itself in phase space. So I will really effectively be measuring correlation function Q equals 0. Now, the point that was our starting point is that in Parisi theory, you would expect that if you sit in this Q equals 0 regime by the Dominici-Skondor-Temesvar in 95, you would expect this correlation function at Q equals 0 to decay as a power law. Okay. Doing that numerically is not, again, completely trivial. So what we do is to compute these correlation functions at finite time. So we say we don't try to go to equilibrium, we have a time, and we are even trying to guarantee you that we are sitting close enough. Sorry, I started from 10 minutes, Stefano, or 15 minutes, 10 minutes, right? I started. No. How much I did talk already? Okay, 15 minutes, very good. Okay, so it was 15, that was exactly my doubt. So I have more 15 or 2. Thank you. Yes, very good. Yes, but I forget mine. So you see, you hypothesize that, so that the dependence over T is somehow this structure. So you have that psi grows with T. So when T goes to infinite, theoretically, you will eventually equilibrate, maybe at infinite time, and you will have a power law decrease. But you have this form, and you assume that the correlation length in time is increasing at the time with some power law, okay? So you do that, and it just works very well. You get good fits. You find that these exponents only weakly depend on T. And you find, for example, that this lambda exponent, the exponent of the growth of the correlation time, of the correlation length with time, is given basically by 0.16 T. Okay? When you go to infinite and so on. So this is our result. This is nice for us because it's compatible with replica symmetry breaking, with normalization group computation. It's really borderline for a kind of non-multiple state picture. Okay, that was typically our decay. The decay is very clear. I don't have to. So we have determined numerically a correlation function, and we've shown it is compatible with the behavior of Parisi theory. And now this is the problem. The problem is that what can be easily determined in numerical experiments is not always, or even very rarely, easy to determine in a real experiment. So, for example, determining a correlation length, a response is something you can easily measure in experiment. You perturb, you see what happens, this is okay, you change the perturbation, but the correlation length, this is far more difficult. So now this is pretty beautiful, since indeed prompted by our paper 4 years later, basically there was Hamman and Vincent group from Paris and Raymond Orbach and collaborators from Paris, I think they were maybe in Texas at the time, introduce a technique in order to do this measurement. Now, I will maybe not enter into much detail. First, let me give you a little sketch, and then I will go a bit more in detail. If I get, let me define the relaxation rate as the derivative, the log derivative, because we are scale here, of basically the thermoremnant magnetization that I will define of a spin glass, okay? What I can do, I can relate directly this rate of decay, to the free energy barrier that you are jumping over. So the speed, the time it will take to get a maximum, for example, of this relaxation of this rate, okay, is connected to the barriers. Basically, you say you have a magnetic field, you change a magnetic field, and this generates an energy that is, okay, there will be h square, we'll discuss that a bit at the end if I will have time. Okay, there will be the field Coulomb susceptibility, that is a number. But also is important is that here it will appear the number of correlated spins that do cooperate in this phenomena. What I mean, if I didn't have a cooperative, a collective phenomena, one spin at a time, clearly there will be no peak at a large time. Everything will happen on the scale of a few picoseconds, I mean, on a really very small time scale. Here, what will happen is that since a number of spin will cooperate, okay, I will have a peak at large time. So there will be a shift, I'm gonna show that, and now you can do the same we did from this numerical data, and the idea is that you find exactly what was found numerically. Let us go a little bit more in detail. So what you do, you cool a sample, I'm doing a disaster, I'm not, you cool a sample in magnetic field, you start from high temperature, go through the glass temperature, go to low measuring temperature, okay, wait a time, T waiting, then cut the magnetic field, and look at the decay of magnetization. This generates a response function that is the derivative of the reaction of magnetization over log T, okay? So, and the idea is that the barrier height gets reduced by the magnetic field. So, I will have a maximum. This maximum would be a T weighting, okay? And this T weighting will be connected to the energy barriers I have to jump through in order to run through my dynamics, okay? So this shows me that there is a peak in the response function, okay? And somehow, maybe I will show it well, what I expect is that when I increase the magnetic field, what do? When I increase the magnetic field, I reduce the size of the barriers I have to go through, and this implies that the peak comes at closer times. So for example, here I show you the response function we determine for different values of the magnetic field. And you see, when I increase the value of the magnetic field, the peak position comes at smaller times. So from that, I can really connect through the formula I told you about. So there is an H square that is the tensor that we discussed a bit close to the end of this talk. There is susceptibility. And then there is the number of spins that are participating to the collective behavior. You see, NS is defined the volume of spins that are really interacting collectively. Okay, so the correlation length will be basically this volume, this number of spins to one third. And I can show you. Okay, this is NS, for example, the number of spins participating, okay, versus log TW. And you see the nice thing, the impressive thing. This number is very small. I mean, you're at very large times, okay, of order of hours, something like that. And this number is of order of 1 million spins. This means a correlation length of 100. So this is obviously asymptotically a bona fide phase transition, but what is happening in the experiment is that really few spins are participating. And this is, so what happened is that indeed, when you go and fit this number, again, you find a few years later, the same exponent we found numerically before. So this gives you, makes you willing of continuing this analysis. This is interesting. Okay, I have 5 more minutes. And in these 5 more minutes, I want to tell you now something recent, because I've been talking about stuff of 25 years ago. But then things have evolved. And there are, for example, 2 recent papers. Then this is a continuous ongoing collaboration. There are even more recent things in which we basically applied the same techniques together with these experimental groups by using all the new things we have, and where we can learn a lot more about that. Still, we will present a situation that is completely consistent with theory. But again, we are learning something even about the way to implement numerics. So 2 joint papers about the Janus collaboration, meaning this Italo-Spanish collaboration, and the Texas experimental group. Okay, these are the 2 papers. Then I told you there are more recent things, but I will not discuss it. So parallel study of non-equilibrium spin glass dynamics, both in an experiment in a spin glass single crystal, I will comment for a moment with you, and in a very large scale simulation of the Edward Anderson model carried out on the Janus 2 supercomputer. Single crystal is important. At that time, spin glasses were available only in powder, while now they can really have huge crystals, monocrystals, okay, of, for example, this material here. That makes measuring cleaner. You can enlarge the field of parameters where you can go and measure and so on. Okay, one uses the zero field quick protocol. And again, this is the other thing I want to tell you, is that here, for example, numerics is learning from experiment. So in this situation, we are doing numerical simulation by trying to use the same, I have 3 more minutes to 30, so I can go. Okay, and yes, so I will do it. Okay, the growth of correlation length is unbounded theoretically, but it's very slow. So at the time I can study, it will be a small correlation length. I've already basically discussed that with you. I don't want to repeat it. It's the same framework I've discussed before, okay? And here you see are, for example, okay, the experimental data. And one of the things you can see is that, so this is a magnetic field. Okay? This is basically the effective time you estimate from the maximum of response function. Is that, for example, there are 2 regions. Okay? One in which scaling is really quite perfectly h square, and one in which, on the contrary, this changes a bit. So one first thing is that you can understand that theoretically quite well. By writing a scaling law, I cannot go in detail, but I mean, log t, so you will have an h squared term, And then when you get to a test pet from operator combination and so on, from replica symmetry breaking, you get to a first correction as this form. Theta is the replicon exponent. Okay, psi is a function of TW, S is a constant, and this function G is of order h to the 4. So basically, this completely unifies a situation where there was debate on the fact that data were not completely consistent with an h-square behavior, that is what we would expect from Zeeman energy behavior, and things work very well. And here, for example, I show you with the same protocol the results you get in experiments and the results you get in numerical simulation. As you can see, the picture is very similar, but maybe I don't want to let me. Yes, what I think is very important is that, okay, you compute these correlation functions, t-dependent, this is what we've discussed before. The volume can now be very large, under 60 to the cube, because we have this powerful dedicated computer. And say, what can basically be my last point is that, you see, for example, the experimental range of the magnetic field used in experiments is of fields that are very small as far as numerical simulation are concerned. There is no way you can use a field that in our dimensional units is 3 in 10 to minus 4 or 1 in 10 to minus 4, okay, in your numerical simulation. But you can use scaling to do matching of these ideas. So, for example, you can say that you can change the temperature in such a way to make the use of this magnetic field more plausible from the experimental point of view. So this leads you to select temperatures, for example, that are closer to T critical of what you use in experiments, okay? And also the second idea, and then I will be done, is that if you use on the x-axis, as basically suggested by Tuliandolo-Kurchan, the correlation function instead of the time itself, scaling laws are satisfied far better. So these are basically pictures of scaling, both experimentally and numerically. And you see that you find a very good scaling for both things, and that somehow this idea of doing a matching, both for protocols, that for the values of the constant you use, makes things far better. There is a lot that we are doing. Maybe what is very important, and I want to stress here, is about temperature chaos, because this is crucial in understanding the structure of the states in Parisi theory. Basically trying and checking how the organization of the state change when you change the temperature, even of a very small amount. The idea is that this can change. And also in that, you can try to match experiments and correlation length. We have 2 papers that came out in the last year. And I think this is an interesting development. Okay. Again, happy birthday, Sergio, and thank you so much.
Thank you, Enzo, for this update about the comparison with experiments of Parisi theory. So we don't have much time, but I think I could allow a very fast question to Enzo. I have one myself. Is the technique used experimentally nowadays the same? So to push the spins across a barrier, or
they use exactly the same technique. What we have a single crystal. Okay, we have better instruments, so we can have more sensitivity and so on. And they are working a lot about protocols.
And how this compares with the 96 experiment? Compares well?
Very well, yes, very well. You learn more, but I mean, these experiments were okay. Okay. Yes, okay. And our simulations too.
Okay.
Okay.
Thank you.
Okay, thank you so much. Thank you so much.